Okay, well, I'm very excited to be here in Atlanta at this conference. I think this is an exciting conference for academic grouping of our athletic brethren. So I'm an Atlanta boy, so I'm also excited to be home. And unfortunately, my parents are still here, so I did have to stay at the hotel. I do tend to walk a little bit as I talk, so if the cameraman can please stay on your toes and please do not zoom in too tightly. Okay, so I'm going to change things up a little bit from the wonderful talks that we've had this morning and just now. And I'm going to not really talk at all about policy, and I'm going to take some of the big picture ideas, and I'm going to zoom down into, as was mentioned before, down into the weeds a little bit. So I am the director of the National Center for Physical Acoustics at the University of Mississippi. I'm also a faculty in the physics department, and that's my training. And so I will take a little bit more fundamental approach to thoughts on, specifically in this case, energy harvesting, than some others in the room might. So things that come out of my lab are not wonderful new devices and fancy little widgets, but more like fundamental understanding of the materials which will then ultimately be used to develop those fancy new devices. Okay, I'm going to start off with this graphic. And the idea with this graphic is to illustrate the point that there is all forms of energy surrounding us all the time. I'm going to call this ambient energy. And so whether it is electromagnetic waves, which are floating around us all through this room, whether it's strain energy with the building vibrations. I was just sitting there a few minutes ago, and I could notice when the air conditioning unit turned on in the building. Well, that's energy associated with that. It's really not going to anything useful. It's just shaking the building. There's, of course, an enormous amount of heat, thermal energy, which is generated from our car engines to factories. And of course, we have ambient light energy all around us as well, from direct solar to the lights in these rooms. So I'll broadly define energy harvesting as the process of capturing this ambient energy, converting it into electrical energy, and storing it for later use. Now, the thing is that I'm jumping to my conclusions already, so you have to bear with me. The thing is that we're never going to power a city with energy harvesting. That's not really the point of what energy harvesting is. Energy harvesting is really more about contributing another component to this ever-widening portfolio of the energy resources that we have available to us. And if you'll remember Dr. Baldwin's wonderful talk, when he was, many of his graphs had legends on the side that went all the way down from the full length of the graph, indicating that there were many components to this energy portfolio. And energy harvesting, I think, can contribute meaningfully to that portfolio. So a quick outline. I'm going to start off with an introduction to what we mean by energy harvesting. I'm not really going to, I took out the slide on motivation because really the motivation was handled beautifully this morning, so I don't want to waste your time on that. I will talk a little bit about the ambient energy sources, how much energy is available in the shaking of this building, how much energy is available in coming out of the heat of the car engine. And I'll talk a little bit about transduction materials. This is more along the lines of the kind of research that we do. So these are the materials which will convert this ambient form of energy into an electrical form which we can store for useful work. Now, some of the specific lines of research that I'll talk about is some work in our lab on thermoelectric materials. I'll do a little bit of concepts of what a thermoelectric is, as well as some work that we have done with NASA recently. I'm going to then hold up a little bit different line of research. It's not my research, but it's a beautiful line of engineering research that uses a hybrid system of thermoacoustic devices with piezoelectric devices to try and convert waste heat into electrical power. And then I will return back to an energies theme in the last part of the talk to talk specifically about a new class of materials for converting strain energy into electrical energy, which are called phase change materials. And this is really more future work than anything else, but it's an exciting line that I wanted to tell you about. And I'll wrap up with some thoughts on applications and deployment. Okay, so where is the energy out there? Where is this ambient energy? Well, we have mechanical energy we've talked about. These are vibrations, mechanical strain, things like that. We've got thermal energy, waste heat, furnaces, heaters. We have light energy, of course, sunlight and ambient light, electromagnetic energy. We have, zooming out a little bit further, all kinds of natural energy, wind, wave, ocean currents, things like that. The human body exhibits an enormous amount of energy as well between motion, heat, things like that. And then there's some other lines of research. I won't talk about any of these at all, really, but in terms of chemical and even biological sources. Now, mainly in the talk, I'm going to focus on those first two bullet items, mechanical energy and thermal energy. Now, before we get there, I wanted to just give everybody an overview of what do we mean by an energy harvester? What are the specific components that are required to take this ambient form of energy and convert it into some useful form, such as electric energy? And so this diagram shows some sort of source of some machinery. The first thing to do is to convert the ambient energy into an electrical form. Now, maybe this particular piece of machinery gets very hot. Maybe it also vibrates significantly. So we've got two forms of energy that we can convert. Of course, that would require two different types of transduction materials. So that's the first stage. And then that energy has to get stored, typically, to get stored for later use. Now, there's also quite a bit of electrical engineering to efficiently convert that electrical power, which is sometimes in the AC, alternating current converted into DC for storage. So there's a fair amount of work just on that component. And then, of course, in the storage end of things, I'm not really going to talk about that so much, but that is extremely important line of research in efficiently storing large quantities of electrical power, so batteries, supercapacitors, things like that. And then finally, we have to get that power to wherever it's going to be used, so the transmission of that power. So if we think about our different forms of ambient energy and the materials required to convert them from their ambient form into electrical, here are some of the options we have. So for thermal energy, there are two main options, thermoelectric materials, which I'll talk about today. There's also a class of materials called pyroelectric materials, which I'll not talk about. For mechanical forms of energy, vibration, strain, and so on, we have traditional piezoelectric materials. But we also have some other interesting forms as well, that is magnetostrictive and electrostrictive materials. I will talk a little bit about electrostrictive materials. And then, of course, for solar radiation, the photovoltaic materials are a wide line of research. I won't talk at all about those today. Okay, let's look at zooming in now into the thermal and the mechanical. Let's look at a few of the advantages and disadvantages. Now, with thermal, the thermal form of ambient energy, of course, there are many sources around, from the transportation sector to the manufacturing sector, and also even engineered forms of thermal energy in the sense of solar concentrators to focus not just the photovoltaic, but also the heating component of that electromagnetic radiation, which can then be converted to electricity using thermoelectrics. These schemes are typically scalable in size, so they can operate from very small scales on up to very large scales. They're also solid state in nature, which is important, meaning there are no moving parts to this. This is just a straight up material property of this class of materials. In other words, there's really nothing to break, very reliable sources. Disadvantages are that the efficiencies are not great. There's a lot of work to be done on the fundamental efficiencies of the energy transduction materials, the thermoelectric materials. I'll talk a little bit about that. Now on the mechanical side of things, we again have many sources, buildings, airplanes. I'll talk a little bit more about that shortly. Also importantly, there are very large sources. Buildings are large, airplanes are large, and so even if they don't have a high energy density, they do have a lot of energy contained within, for instance, the whole structure. Okay, so I'll get a little more quantitative about that shortly. Also, on the mechanical side, we have the benefit of some interesting new materials and not so new materials. One of them is a polymer-based piezoelectric material, which really increases your opportunities for application, for instance, in clothing and things like that, which you really wouldn't want to put a rigid ceramic material in. Like I said, some disadvantages are the power densities. The power densities are not very high with ambient strain, typically, although, of course, that is, varies widely depending on the specifics of the situation. But they do, the high efficiency transduction materials for piezoelectrics particularly are typically very brittle, and that is problematic. Because once these transducers break, then they really lose their efficacy completely. And so that presents some challenges. Now let's get a little bit more quantitative about the energy densities and power densities. So now again, if you look at something like vibrational, I pulled these numbers from this report that I've referenced here, a very good report coming out of Los Alamos in 2007 and later published in the Journal of Infrastructure Systems a year later. If you look at, you say, well, okay, I've got all this energy, this vibrational strain energy in structures such as this building. Well, how much energy is really there? Well, that depends a whole heck of a lot on where it is in the building you look. So if I say something like 200 microwatts per cubic centimeter, so a cubic centimeter about the size of a sugar cube, let's say, so 200 microwatts in that amount of volume, then that number is maybe something that's representative, but you need to, of course, take it with a grain of salt. So a little more representative, the range that we can discuss is in the next column over under demonstrated optimal output. And so these are, when I say demonstrated optimal output, these are actual tests that have been done to see how much power we can get out. So on the order of 4 microwatts per cubic centimeter based on human motion, up to about 800 microwatts per cubic centimeter with frequency ranges in the kilohertz range for machinery. So that really gives you a little bit better idea of the sort of range that we're talking about. Thermal gradients for which we would use thermoelectrics, something on the order, power densities on the order of 150 microwatts per cubic centimeter, with demonstrated optimal output at about 60 microwatts. So right there you can see that we've got a bit of an efficiency problem. And for comparison, I'm not really going to talk about this, but I've listed a few other things. So direct solar photovoltaic gives us a power density on the order of about 15,000 microwatts per cubic centimeter. And indirect solar about several orders of magnitude less than that. And just for fun and for Dr. Cron's sake, I put in our nuclear energy density, which is, of course, way off the charts, into the millions of microwatts per cubic centimeter. Okay, so let's zoom in and we'll talk a little bit about thermoelectrics. So the idea with a thermoelectric material is that it is able to convert a thermal gradient, that is a hot side and a cold side, directly into an electric voltage. In order for this to work, now respectively, it can work in either way. It can either work by taking a thermal gradient and producing an electric current, so we might call that a power generation mode. It can also work the opposite way. I can pass a current through and I can create a thermal gradient, so I can use it for refrigeration, chilling, heating, things like that. Respectively, these are the Seebeck effect and the Peltier effect. You probably have heard of Peltier coolers. So of course, we're going to focus on the power generation mode. And so there are two types of materials. Well, the thermoelectric has to come in two forms depending on the leg, they say, of the thermoelectric device. There has to be an N-type and a P-type. So one type that has an excess of electrons, and one, that's the N-type, and the other type that has an excess of holes, that's the P-type. In order for the thermal gradient to drive those charges in different directions. Okay, so that's a very quick introduction into thermoelectric materials. Some applications here are power generation. Of course, that's what we're mostly going to talk about. Now, our particular work that I'm about to show you was with NASA, and NASA likes to use thermoelectrics to power its deep space probes. Now, way in deep space, the power density for solar is not nearly enough to power the onboard electronics to send signals back. So what they do is they put a radioisotope thermal generator on board. So this is a small hunk of radioactive material. It generates a fair amount of heat. They coat this thing with thermoelectric materials. That's the hot side. Of course, the cold side, we've got deep space, which is great. It's very cold. So we're able to, this is how that they power their onboard electronics. Extremely reliable power source. I don't believe they've had any failures, and I think Cassini maybe was the first spacecraft to use this. So they're looking for next generation thermoelectric materials. Now, when we talk about thermoelectrics, when you're in that community, the holy grail is the figure of merit. So this is a measure of how efficient the material is at converting the thermal energy into electrical energy. And it's called, in the vernacular, it's ZT. I have an equation here, so I may be the first to show an equation, so I hope that doesn't put you off. So the equation shows us how we calculate ZT. We want to get that up as high as possible. So there's some material properties here. There are sigma, which is the electrical conductivity of the material. S is the thermopower of the material. Again, a fundamental material property. T is absolute temperature. And KT, or kappa T, is the thermal conductivity. So you look at this and you say, well, okay, I want to maximize ZT, so I maximize the numerator, I minimize the denominator, and bang, I just pick out materials that have those fundamental properties, and I've got a great thermoelectric. The problem comes in the fact that the electrical conductivity and the thermal conductivity, that's sigma in the numerator, kappa in the denominator, are going to fight each other, because the thermal conductivity depends also on the electronic. Has sort of two parts to it. It has the thermal conductivity that's heat that is transferred by electronic means, and that which is transferred through the lattice of the material, the structure of the material. And so the problem here comes that if I increase thermal conductivity, then I also increase the electrical conductivity. So those two fight each other, they offset each other. This is why metals are both good conductors of electricity as well as conductors of heat. Their primary mode of thermal conduction is through electronic means. So it takes a little bit more creativity. And the plot there that comes out of the Snyder group at Caltech And the Jet Propulsion Lab shows several classes of thermoelectric materials, some fairly exotic, some not too exotic. The YMS ones are circled. We were mostly interested in ones that had maximum ZT values in the in the high temperature range. Now, in order to be competitive, these ZT values need to be on the order of 3 or 4. Right now, they're 1. Okay, so we've got a ways to go on the fundamental materials in order to get to make thermoelectrics really competitive with other forms of energy scavenging. So that's the material efficiency. There's also the device efficiency. Now here we get into some fundamental thermodynamics about how efficient can you actually make an energy conversion, and it's not 100%. And so when we do some calculations, this is a rough estimate of how we might calculate the overall efficiency of a thermoelectric device, which has the temperature difference between the hot and the cold side factored in. Now gamma there has the ZT, or the figure of merit. That's the material efficiency coming into play. And the plot there shows the efficiencies as of the thermoelectric device as a function of this figure of merit ZT value. And you can see that they increase as ZT goes up. So, and also the family of curves broken down by color. The difference there is holding the cold side at 300 Kelvin. So I'm a physicist. I'm going to work in Kelvin. So absolute scale. So 300 Kelvin is what it is in this room right about now. That's room temperature. So going up to the hot side, that's what changes with the family of curves. And you can see the most efficient, the hotter the hot side is, the bigger the temperature difference, the more efficiency I get. So really to maximize our output here, we want to apply these materials to the hottest heat sources that we possibly can. That increases not only the overall power, it also increases the efficiency. Okay? And so in order to apply these materials at very high temperatures, now granted, remember we're talking about NASA and this, talking about these very high heat sources, but it's not that hard to get up to 800-900 Kelvin. We need to understand the mechanical properties. So this is where we come into play. In our group, we use a method called resonant ultrasound spectroscopy that we can make very precise measurements on elastic properties of materials. In our particular lab, we focused on high temperature and high pressure extreme environments. And so I'll not spend much time at all on this slide, but the idea here is we take a little sample of a material and we drive it with a piezo, and it resonates, it rings like a bell. Those frequencies there, the peaks that you see are a typical spectrum of resonances that we get for a sample. From those resonances, we can back out the full elastic tensor of the material. So this might just be Young's modulus, shear modulus, but in a single crystal, it might be a full nasty tensor. Okay, we're able to do that. Elastic constants turn out to be a great insight, provide great insight into a material. They essentially boil down to how are the atoms or the subunits of that material, how are they bonded together? What is the nature of their interaction? And it's just the curvature of that potential energy well. And so if there's any change in the material, it's going to show up in the elastic constants. So that's the fundamental physics side of me is excited about that. But it also turns out, of course, that the mechanical properties are enormously useful and important for engineering applications. We need to know what the mechanical properties are at 1,000 degrees Celsius, for instance, if that's the application. And we sure as heck had better not extrapolate into those temperature ranges based on lower temperature ranges, because I have seen way too many times that the extrapolations very well may not work. So we need data at these high temperatures and pressures. Okay, so specifically, I'm going to move on a little bit quicker here. We looked at some silicon germanium alloys, both N-type and P-type, doped. These were made at the Jet Propulsion Lab in the Thermoelectrics group. And we measured the elastic properties as a function of temperature, and the P-type does just what you sort of normally expect. It softens a little bit as it gets hot. The temperature scale is in Kelvin, but I can tell you the highest temperatures there are at about 1,000 degrees Celsius. Aluminum melts at about 600 degrees Celsius, to give you some reference. This is pretty hot. And so it just nicely smooths, it smoothly softens. However, the N-type shows something that's very bizarre. It shows a softening and then an abrupt stiffening. And then if we cool it back again, it doesn't follow that same temperature trend. So there's some hysteretic effects here. And then if we heated it again, it doesn't follow the original heating trend. It follows the path that it just took. And so this is one of those examples that was very surprising behavior. We also see some similarly anomalous behavior in the electrical resistivity as shown in this graph. And so we figured out what the problem was, is that in the N-type, the phosphorus atoms were actually diffusing out of the crystal lattice. They were precipitating. This was unexpected. And so the problem here is that if you didn't know this, then the efficiency of this material as a thermoelectric device becomes severely affected by this effect. So I hold this up as an example of highlighting the importance of actual measurements in getting data for these materials in these extreme environments. I'm going to quickly go through this. This is the thermoelectric piezoelectric hybrid device, and this is some work done by Robert Keolian out of Penn State and Scott Backhouse at Los Alamos. This is a fantastic piece of engineering. The idea here is that we take hot exhaust and we are, through something called the thermoacoustic effect, we're able to convert that heat into a standing acoustic wave, a very powerful standing acoustic wave if we hook up to a resonator. The pink sections here are where the hot gas would come in and go out, and then the gray is the enclosed acoustic resonator. So if we put membranes in piezoelectrics where those pressure nodes, antinodes are, then turns out they can generate a significant amount of electric power. And so here's a prototype. This is a small prototype showing about 37 watts of output. And they are working on working with Volvo to use these things on semi-tractor trailer exhaust systems. The calculated output is going to be something on the order of 4 kilowatts. Now we're talking about some real power, some energy savings, fuel savings. Now, the last thing I wanted to briefly touch on is vibration and strain energy harvesting. And so there's a lot of fantastic work that's going on in this field, and that image there comes out of Dr. Wang's group at just down the road at Georgia Tech on micro and nano generators. The work that we're thinking about moving into involves something called relaxer ferroelectric materials. And these are materials in which undergo a pressure-induced phase change from I'm going to scoot onto that one, from a certain crystal structure, rhombohedral for instance, into a different crystal structure, in this case tetrahedral. And they can, with a little bit of strain, they can oscillate. They can slosh back and forth between these two phases. And the thing is that when that phase happens, a polarization vector occurs. It reverses, depending on which direction we're going in the transition. And so now we have an electric voltage across this. And it turns out that the measured energy density you can get out of these things is something like a factor of 100 higher than traditional piezoelectrics. So this is an area that we are beginning to look into, mapping out the fundamental physics, the phase diagrams of these phase change materials. I will probably skip over a little bit of the application stuff and zoom right to the conclusions. So like I said at the beginning, we're never going to power our cities with these methods, but we sure can meaningfully contribute to the overall energy portfolio in terms of efficiencies and savings for other forms in our energy portfolio. I say here that we've picked the low-hanging fruit, and I think I need to qualify that a little bit. On the material side, we've picked the low-hanging fruit. I think there's a lot of low-hanging fruit on a broader scale that we've yet to pick. But on the material side, we need to start getting a little bit more clever about our fundamental understanding of the materials, the cleverness of our engineering designs. And I'll end with this last bit to go forward is not only must we improve these things, but we also need to keep in mind that we have to create solutions which are not cost prohibitive. If I create a wonderful thermoelectric material that has a ZT value of 10, but it costs $10,000 for a gram, that really doesn't do anything to help move us toward or away from a carbon-based energy portfolio. So with that, I will close with some acknowledgments. Thank you to the grad students that have helped support this work, my sponsors, and also especially the organizing committee for inviting me to speak. Thank you.
We'll take 2 or 3 short questions. Oh, there's a hand.
Hi, my name is Will Benton. Great presentation.
Thank you.
My question was, I haven't known anything about this before until now, but a thought crossed my mind. Being able to harvest energy would lend itself to nanotechnology where you have to have a outsourced energy and you can get that from a host body. Is that possible?
Say the middle part, nanotechnology, and what was the part after that?
Harvesting energy from the host body.
Right, well, so nanotechnology is a very important component in the current research in these energy transduction systems and materials. You're absolutely right. And the fact is that a lot of these systems, Dr. Wayne's group, actually, I highlighted there, he's done some fantastic work with miniaturizing these little conversions, these micro and even nano level generators. And that opens up a whole host of possibilities in terms of applications. Now I can do things like, sew them in the elastic of my underwear, for instance, and I can actually get some useful energy to power my iPhone. Okay.
Wow, that was quite an image there. There's a hand back here.
Hi, I'm Brian Conlon from University of Tennessee. I know you had some of the application stuff built into your presentations. I was wondering if you could speak to some of those.
Well, the applications are so broad, it's hard to, even in the limited time I had here. But in terms of applications for strain energy harvesting, you look at anything that shakes is a potential application. So, you look at those, for instance, those air conditioning units that are out there that are mounted on rubber. What do? They mount them on rubber mounts. And why do they do that? To dissipate the vibrational energy, right? In other words, thermalize it, lose it, get rid of it. So the point is here, let's not get rid of it, let's capture it, and then let's store it, and then let's use it to power these lights, okay? But also walkways down, in high traffic areas. Well, that's pressure, that's energy, okay? Let's put some piezo, all in those walkways and power the lighting for that building, for that walkway, okay? Just to name a few. We could go on for a long time, but there's another speaker. Yes?
Last question over here.
You're in the southeast as well, but with all our buildings in the southeast, we have an abundance from air conditioning with chillers of a 90 to 100 degree water. What can we do with that low heat source, low temperature heat source?
Right. Well, in terms of the vibration side, we've talked a little bit about that, but from the heat side, capturing maybe some of the waste heat coming off of there, still there's, I think, for instance, this thermoacoustic device might have some potential It's not a sort of universal application device, obviously. I think thermoelectrics really have a ways to go. We really have to understand and get a grip on the fundamental materials physics in order to get the efficiencies high enough for it really to be widely deployed on an energy scavenging applications.
Okay, let's thank Josh for a nice talk.
Thank you.